A soft, e-skin that can mimic the sense of touch. Receptors in human skin can sense the weight of a butterfly, the heat of a flame, or the cold of a cold drink. Thanks to them, we can even feel our pulse, even with a gentle touch. Engineers have long been developing materials that mimic this sense. Now, for the first time, they have succeeded in creating an e-skin that allows us to feel heat or pressure and can communicate directly with the brain. Mechanoreceptors found in human skin are responsible for the reception of mechanical stimuli such as touch, vibration, or stretch. An external stimulus changes the membrane potential of the receptor, which generates a nerve impulse that reaches the central nervous system. Scientists at Stanford University have successfully developed soft integrated circuits that convert detected pressure or temperature into electrical signals similar to nerve impulses. This enables the e-skin to communicate with the brain. Scientists hope that one day, these signals could be directed to implanted chips in peripheral nerves. This technology could lead to the development of a coating for prosthetic limbs that would mimic the sense of touch, giving users the ability to feel heat or pressure. It could help restore some sensation to people whose skin has been damaged. Other potential applications include new implantable or wearable medical devices. Such an e-skin could also enhance virtual reality experiences. The discovery was reported in the journal Science. We have been working on e-skin for some time. The main obstacle in this work was not so much finding mechanisms that mimic the extraordinary sensory abilities of human receptors, but connecting them using only skin-like materials, explains Jinan Bao, professor of chemical engineering and lead author of the study. The researchers explain that the challenge was to improve skin-like electronic materials so that they could be incorporated into complex integrated circuits that could generate impulses similar to nerve impulses. The material also needed to have a low enough voltage to be safely used on the human body, says Wei-Chen Wang, a doctoral candidate in Bao's lab. Wang worked on the e-skin prototype for 3 years. The researchers therefore sought a soft integrated circuit that could mimic the mechanisms of sensory receptors and operate efficiently at low voltages. However, Wang's initial attempts required 30 or more volts and could not provide sufficient circuit functionality. The new e-skin operates at just 5 volts and can detect stimuli similar to real skin, explains Wang. Artificial skin will be crucial for next-generation prosthetic limbs, which will be able to restore not only movement, but also a partial sense of touch. Most e-skins are composed of multiple layers of materials resembling real skin. Each layer contains organic nanostructures that transmit electrical signals. These networks can be designed to detect pressure, temperature, stress, and chemicals. Each such layer has its own integrated circuit. 6 similar sensor layers are then combined into a uniform material that doesn't delaminate, tear, or lose its electrical function. The finished material is no more than a micron thick. However, this layer is too thin to be easily handled. Therefore, we use a special substrate, which increases the thickness of our e-skin to approximately 25 to 50 microns. This is roughly the thickness of a sheet of paper. Human skin has a similar thickness, explains Professor Bao. This is the first material that combines all the desirable electrical and mechanical properties of human skin in a soft, durable form, and can be used in next-generation prosthetic skins. With this material, scientists hope to develop innovative human-machine interfaces that could provide a sense of touch to people with prosthetic limbs. The eyes of deceased individuals reacted to light. Scientists have revived photosensitive cells. Scientists have revived light-sensitive neurons in eyes collected posthumously from organ donors and restored communication between them. This is part of a larger series of experiments that could transform brain and vision research. This research also opens up new possibilities for transplantation and questions the irreversible nature of death. Billions of neurons in the central nervous system transmit sensory information in the form of electrical signals. In the eye, specialized neurons called photoreceptors sense light. A team of scientists from the John A. Moran Eye Center at the University of Utah and researchers from Scripps Research used the retina to study how neurons die. They also tested new methods for reviving them. We were able to awaken photoreceptor cells in the human macula, which is part of the retina.
Pas de soleil, pas de soleil, pas de soleil, da-da-da. Pas de soleil, pas de soleil, pas de soleil, da-da-da. du soleil.